Okay, so hello everyone, I'm Andia. Today I'm going to talk about a scenario for quark collapse supernova explosions, which was mentioned in the very first lecture of this symposium, which is quark collapse supernova that are driven by first-order QCD phase transition. So I would like to start my talk with a phase diagram. Okay, let me see if the pointer works. Do you see? Okay, perfect. So I would like to start with a phase diagram showing the temperature in the y-axis and the net baryon density. All the matter that has been discussed so far is lying in the hadronic branch, so the normal, the hadronic matter. While we have experiments like LHC in CERN that explore high values of temperature, but low values of density, and they see a crossover from hadronic matter into quark-gluon plasma. However, at high values of net baryon density, one cannot explore this in terrestrial experiments. So in other words, if I want to show regarding to the instability, the speed of sound is what I want to show. In hadronic matter, you see the values of speed of sound squared less than 1/3. And from the asymptotic value of quark-gluon plasma, we know that this reaches the value of 1/3. So we already have, as you know, observations from two solar mass neutron stars, and that indicates that the speed of sound should be more than 1/3, which is shown here. And this indicates that there should be some non-monotonous behavior of the speed of sound, and that indicates a QCD phase transition. Which order, we don't know. So in the low values of density, as shown here, calculations of, for instance, in this case, chiral effective field theory, there are some constraints. Also, for very, very high values of baryon density, we have calculations from perturbative QCD. And how to connect these two regimes is model dependent. So there are lots of models exploring this non-monotonous behavior of speed of sound, and they do not necessarily have to go to arbitrary high values. Even in the, let's say, more moderate behaviors, we see that the mass radius relation of neutron stars that comes out of them are in qualitative agreement with the observations, both for the masses and for the radius that we know from the pulsars and also from the gravitational waves. So now the idea is, if we can probe this possibility of having a first-order phase transition from the hadronic matter into quark matter. And for that, one of the best conditions, extraterrestrial, of course, to explore this idea is quark collapse supernovae. So the input, which is the equation of state, as you can see here, the hadronic equation of state that is used with all the models that we have seen so far, one of them is shown here in the dashed line. And having a quark equation of state means that with a first-order Maxwell construction, means that we connect the quark equation of state by a density jump at a certain value of pressure. This is calculated for 0 temperatures. However, you know that we don't deal with 0 temperatures in quark collapse supernovae. So at a fixed value of entropy per baryon and a fixed value of lepton fraction, you see the same equation of state shows the onset density of phase transition at much lower values, and the jump is at much larger compared to the 0 temperature case. So taking this kind of equation of state into account gives us simulations. So in this case, I'm showing you results from a simulation that is spherically symmetric, but we are treating the transport with Boltzmann transport. Now, what happens if you have the input of the equation of a state that goes through a first-order QCD phase transition? As you can see in this movie, the matter velocity shows that there will be a collapse after the shock stalled, and this collapse makes a shock forming, taking over the first shock, and then pushes the matter to the interstellar medium. You can also see here the quark fraction, which starts at non-zero, non-off-center values. And then when the quark fraction is sufficient enough, then the collapse happens. And maybe I can, okay. Maybe I can show this again. So, and for the color coding that you can see here as an example is the electron neutrino spheres. So these kind of explosions, if you want to take a look into the shock evolution of them, the dashed line here is the bounce shock. So, oops, you can see that, yes, here, if there will be no QCD phase transition, since we are taking into account spherical symmetry, this would just continue. So there will be eventually a black hole formation. However, by having this first order phase transition, a second shock forms from the core, takes over the first shock, and then pushes matter into interstellar medium by orders of magnitude. And as you can see, the entropy per baryon here, color-coded, is high enough to have our process elements even after this kind of explosions. The dashed dotted lines are the protoneutron star radius, which you can see after the phase transition is even more compact. So regarding the observations, the explosion energy that comes from these kind of simulations is in the order of 3 × 10⁻51 ergs, which is in agreement with the observations so far. And the remnant mass of such explosion is also in the order of 2 solar masses, which is also in agreement of the mass measurements we have seen in observations. In this particular case, we see that around more than 1.5 solar mass of this configuration is quark mass. And I have to also note that this matter is, the matter velocity shown here is highly relativistic. So now, what is the feature that makes this scenario distinctive from the so-called neutrino-driven explosions? There will be a second shock. So as you can see here, the red lines, which is the electron neutrinos, this is the burst that has been shown before for the neutrino luminosities in previous talks too. There will be a second shock when the phase transition happens. And in this one, since the matter is already neutron-rich, this shock is dominant in electron antineutrinos. So there will be a second burst, which is to the high values. And also you can see this in the average energies. Now, regarding the detectability, with rather pessimistic binning time of 2 milliseconds, this second burst can be seen. Even though this is a very narrow band, still the aftermath is qualitatively high. So this can be, in principle, detectable within, of course, galactic supernova, 10 kiloparsec, more or less. So, of course, not every simulation leading to an explosion. We also have black hole formations for these different equations of state. And what was interesting was that we saw 2 different scenarios for the black hole formation case. So the ones that are prompt, as you can see, there is a second shock forming. So these different lines differ to different times. And but the shock doesn't move. So that in the center, we have the black hole formation, the Labs function goes to lower values, but the shock doesn't move forward, which we call the prompt collapse. But for the delayed case, you can see here that even though we have a collapse into a black hole, the shock that has been formed due to the phase transition keeps moving forward. And in some cases, it even takes over the accretion shock that we had from the first bounce. Okay. So now what can we learn from these scenarios regarding the observations? As I mentioned, so these different models, so I varied different progenitor masses, different equations of state. And these, in this case, you can see for one of the progenitors, 3 different equations of state that have different parametrizations. And I normalized the time of the collapse, the second collapse, which leads into the second shock. And as you can see, the second burst happens at different times. So this is model dependent. Depending on when this phase transition happens, the time of the collapse is also different. So different progenitors starting from 25 solar masses up to 75 solar masses with different equations of state which go through the first order QCD phase transition gives us different values of burst. So this is related to the second burst of electron antineutrinos. And the luminosity peaks are shown here, the average energies of electron antineutrinos and the explosion energies. At the first glance, it might look random, but if we plot, for instance, the onset of collapse, so the density, the central density of the protoneutron star when it collapses to the burst time, you see a linear correlation, which is more or less trivial. So these equations of state that are shown here, this model has a lower onset density for phase transition compared to the ones that are here. And therefore, at shorter time, we reach the density that leads into the explosion. Now, taking a look at the peak luminosity and explosion energy, we also see a linear relation that shows the higher the explosion energy, the higher the neutrino luminosity peak, and vice versa. And now, connecting these into the luminosity peak and the onset of collapse, so the density that the protoneutron star collapses, shows another linear relation. So the message here is that if there will be a detection, and if there will be the second shock, one can actually constrain the onset density where the protoneutron star collapses. And this can put a constraint on the equation of the state when we have this QCD phase transition. And even if it doesn't happen, also this constraints at what densities we cannot expect the first order QCD phase transition. I showed here also the average energies, because this is more related to the detection. And we see also this linear correlation for that too. Of course, this is not the only multi-messenger from core collapse supernovae, so I will talk about also the gravitational waves. There are simulations done by Kuroda et al. And Za et al. With these equations of state, and you can see that when the phase transition happens, we have a very loud amplitude due to the first order QCD phase transition. And also for the frequencies, you can see how loud it gets. So this is something that could be detectable also for the gravitational wave analysis. So since I am before that, regarding detectability, let me show how these three different scenarios look. So the neutrino-driven explosion is shown in black. Then we have the failed supernova, 70 solar masses in blue, and then we have the one that is exploding due to the QCD phase transition in red. And you can see how loud, even it's louder than the failed supernova simulations. And they're all within the detectability region of the current detectors. Okay, since I'm dealing with 1D simulations, of course, I cannot take a closer look to the gravitational wave analysis, but what I can do is to do some mode analysis, so some linear perturbation theory, which has been discussed in detail by Alejandro today. I use the same numerical tool to see what can we learn regarding the modes, how would they behave, and if there is some differences regarding the standard scenario and the QCD scenario. So in this case, I normalize them at the onset of explosion. So you can see here the gray ones is the neutrino-driven. There is the fundamental mode if we assume of the, let's say, the conversion that's mentioned by Alejandro. So assuming that the frequency starting from here and then the avoided crossing continuing here, this is the fundamental mode. You see that it starts from less than 500 and then it reaches somewhere around less than 1,500 after 3 seconds from explosion. While for the QCD driven, we see the same feature starting from less than 500, the avoided crossing, and then at some point we have the QCD phase transition. So then there is a sudden jump at the frequencies, and then the fundamental mode continues here. So this is something that is in agreement with different models that I have checked. So there is a sudden rise in the frequency for the F mode. And also there are some peculiar behaviors also for the G mode here that is shown. And of course, the decreasing G mode that was mentioned in the other talks is also visible both for the QCD case and for the neutrino-driven case. So based on the letter that also has been done by Pablo and Alejandro, we can actually find correlations between the mean density for the fundamental mode and also for the compactness for the G modes. And that's why I took the challenge to check if we can find some fits for this, which is in agreement. What I also want to show here is that this dashed dotted line is where we have the first onset of QCD phase transition when we have some off-center values of quark matter appearing in the star. However, as you can see, it takes around 150 milliseconds until we have the collapse and then having the second shock formed, and of course the frequency at higher values. So this is not happening in a fraction of a millisecond. So for the black hole formation case, you can see that this kind of analysis with the GREAT tool I zoomed in here so to show that in the very last tens of milliseconds, since we are assuming static background, this would probably not be reliable. But also for the QCD phase transition black hole formations, we see this sudden rise of the frequencies for the onset of black hole formation. G modes are a different story, of course. So as a summary, I just want to show, I hope I could convince you that if there will be this exotic phase of having a QCD first order phase transition, there are signals that one can probe this. In the talk, I talked about the mode analysis, how we will have a feature that is a sudden rise in the frequency for the fundamental mode, and also the linear correlations that we have found regarding varying different models, different progenitor models and equations of state. But I also would like to take the chance to tell you that there are also other astrophysical sites to probe. In this case, an accreting induced collapse of a neutron star, which is at the onset of QCD phase transition. And in this case, you can see that at around, let's say, 4 milliseconds, the phase transition happens. And then that also changes the mode behavior due to the phase transition, which is a different, of course, astrophysical explanation, which I do not have time to go to the details. But with that, I would like to thank you.
Questions?
Isn't physics fun? Beautiful, beautiful work too. I was just curious. How are you modeling the QCD equation of state?
Okay, so this is a work that has been done by Niels Ove Bastian during his PhD.
Oh, okay.
So it's a whole different story. There are lots of parameters, and this is just, let's say, one quark equation of the state.
Okay.
So we are not changing that. The only thing that is changing in these 9 models that we have explored is with which hadronic equation of the state correlates to this quark equation of the state, and at which density the transition happens. So this is what varies. Of course, there are lots of parameters, but these are the bulk ones.
Okay. I was just curious if it was running up against constraints, experimental constraints.
No, it's in agreement.
It's in agreement.
Yeah,
Okay, good.
This has been checked.
Yeah.
Okay, David.
Thank you. So from what I recall from the Shui Jia and the Connor papers, where I looked at this something similar, the first order hadronic quark phase transition, the claim there was that you need to be above 3 to 9 times the nuclear saturation density to begin the hadronic quark phase transition, and then you become fully quark matter at around 9 times. But in the quark collapse order simulations, we don't reach high enough densities to trigger this phase transition. Has that changed since?
So I'm quite surprised to hear that high value that you just mentioned now. But what I show here, for instance, you can see that I have to show here. So in the TCO0 case, the onset density is around 1 × 10⁵. So let's say, of course, this is model dependent, but it's not, I mean, maximum 2-3 times saturation density. It is valid. It's a valid density range for the supernova. Of course, I know that in the neutrino-driven phase, we do not get that dense, but the idea is that simulations are long enough that the star gets to these densities that would go through this phase transition. but not like, I don't know, 10 times, 11 times saturation density. That's probably too far.
Saturation density is a function of the composition. So saturation density is less than what it is for symmetric improvement.
Yes.
So is this indicate 10 to the 15 things?
This is 10 to, so this is around this 1 times 10 to the 15 gram per cc. Yeah.
That's probably 6, 7 times nuclear saturation.
But one has to take into account that when we have the temperature effect, the onset density goes to even lower values. So you see the one that is in T equals 0 around 1 times 10 to 15 now here is around 0.4, less than 0.4, 10 to the 15. So it comes to lower values due to the temperature effects.
Yeah, David's question is related. Because when we first did this, as you know, in 2009, with heat and 6 figure,
Yes.
The parameters, the equation state parameters, were chosen at the edge of what was experimentally allowable in order to have this happen. But
right, but that was a bag model. So this is just so this model, the quark equation of state is more advanced than that by far. Yes. So it is still a mean field approximation, but connected to the different, yes.
Okay, I think we can move to the next talk. So let's thank the speaker again.